CSC159. Computer Organization. Chapter 5, Interfacing and Communication. Prepared by Sidi Fatima Noor Abwahab. What will be covered in the whole chapter? Peripherals. I/O considerations, speed and coordination issues. I/O modules. Programmed I/O. Interrupts. Direct memory access. Stacks, little endian, big endian. CPU, memory, I/O architectures, bus architecture, channel architecture. Chapter 5. Part 1. Peripherals. Basic model of a computer system. Types of peripheral devices. I/O considerations. Case 1 to 5. Examples of I/O devices categorized by a typical data rate. I/O consideration for different I/O devices. I/O modules. Simple I/O configuration. More complex I/O module. I/O module major functions or requirements. Example, functions of disk controller, an I/O module. I/O module interface. Buffering. Handshaking. Peripherals. Introduction. A peripheral device is an internal or external device that connects directly to a computer but does not contribute to the computer's primary function, such as computing. It helps end users access and use the functionalities of a computer. Peripheral devices demand the attention of microprocessor at various and predictable times during normal program execution. Several techniques are combined to resolve the problem of synchronizing and handling I/O between a variety of different I/O devices. Basic model of a computer system. Processing speed or program execution. Determined primarily by ability of I/O operations to stay ahead of processor. This figure shows the input process output, IPO, model that represent the work performed by an individual computer system within the IT system, which can be characterized by input, process, and output. Types of peripheral devices. Peripheral devices can be in different types according to their connection type to the system and data transmission direction. There are three main different types of peripherals. Input, used to interact with, or send data to the computer, mouse, keyboards, etc. Output, which provides output to the user from the computer, printers, speakers, monitors, etc. Storage, which stores data processed by the computer, hard drives, flash drives, etc. The other one is communication or network, which is used for interaction, modem, web camera, etc. I/O considerations. Speed and coordination issues. Case 1, Keyboard. Consider, for example, the keyboard as an input device. The keyboard is basically a character-based device. Typing on the keyboard of your PC results in Unicode or ASCII input to the computer, one character at a time. Even mainframe terminals, many of which can send text to the computer a page at a time, only transmit a page occasionally. Therefore, the data rate for keyboards is obviously very slow compared to the speed at which the CPU processes the data. Case 2, Mouse. Another input device that will generate unexpected input is the mouse. When you move the mouse, you expect the cursor to move on the screen. Clicking on a mouse button may serve as expected input to a program, or it may be unexpected and change the way in which the program is executing. In fact, unexpected input is fundamental to programs written in modern event-driven languages such as Visual Basic and Java. When the user selects an item on a drop-down menu or clicks on a toolbar icon, she expects a timely response. Again, data rates are slow. Case 3, Printer and Monitor. Printers and display screens must operate over a wide range of data rates. Most modern output is produced graphically or as a mixture of font descriptors, text, bitmap graphics, and object graphics, a page or a screen at a time, using a page description language. The choice of page description language and mixture of elements is determined by the capabilities of the printer or graphics card. Clearly, output to a printer consisting only of an occasional page or two of text will certainly not require a high data rate regardless of the output method used. Case 3, continued. The output of high-resolution bitmap graphics and video images to a monitor is quite a different situation. If the graphics must be sent to the graphics card as bitmap images, even in compressed form, with data for each pixel to be produced, it may take a huge amount of data to produce a single picture, and high-speed data transfer will be essential. A single, color image on a high-resolution screen may require several megabytes of data, and it is desirable to produce the image on the screen as fast as possible. If the image represents video, extremely high data transfer rates are required. Case 4, Disk or image devices. Disks are used to load entire programs or store files of data. Thus, disk data is always transferred in blocks, never as individual bytes or words. Disks may operate at transfer rates of tens or, even, hundreds of megabytes per second. As storage devices, disks must be capable of both input and output, although not simultaneously. On a large system there may be several disks attempting to transfer blocks of data to or from the CPU simultaneously. Therefore, the computer must be capable of transferring massive amounts of data very quickly between the CPU and the disk or image devices. Clearly, executing a single instruction for each byte of data is unacceptable for disk and image I/O, and a different approach must be used. Case 5, Networking devices. From the perspective of a computer, the network is just another I/O device. In many cases, the network is used as a substitute for a disk, with the data and programs stored at a remote computer and served to the local station. For the computer that is acting as a server, there may be a massive demand for I/O services. User interfaces such as X windows, which allow the transfer of graphical information from a computer to a display screen located elsewhere on the network, place heavy demands on I/O capability. Examples of I/O devices categorized by a typical data rate. This table shows a typical data rates for various I/O devices. The values given are rough approximations, since the actual rates are dependent on the particular hardware systems, software, and application. As computer technology advances, the high-end data rates continue to increase at a rapid pace. I/O consideration for different I/O devices. The formats required by different devices will be different. The incompatibilities in speed between the various devices and the CPU will make synchronization difficult, especially if there are multiple devices attempting to do I/O at the same time. I/O devices and the interconnections that support multimedia services must be capable of guaranteeing steady performance. Devices such as disk drives have electromechanical control requirements that must be met, and it would tie up too much time to use the CPU to provide that control. I/O modules. Simple I/O configuration. The different requirements for each I/O device plus the necessity for providing devices with addressing, synchronization, status, and external control capabilities suggest that it is necessary to provide each device with its own special interface. Thus, in general, I/O devices will be connected to the CPU through an I/O module of some sort. The I/O module will contain the specialized hardware circuits necessary to meet all the I/O requirements that we established, including block transfer capability with appropriate buffering and a standardized, simple interface to the CPU. At the other interface, the I/O module will have the capability to control the specific device or devices for which it is designed. The simplest arrangement is shown in this figure. More complex I/O module. I/O modules may be very simple and control a single device, or they may be complex, with substantial built-in intelligence, and may control many devices. A slightly more complex arrangement is shown in this figure. The additional I/O modules require addressing to distinguish them from each other. The lower module will actually recognize addresses for either of the I/O devices connected to it. I/O modules that control a single type of device are often called device controllers. For example, an I/O module that controls disks would be a disk controller. I/O module major functions or requirements. The major functions or requirements for an I/O module fall into the following categories. Control and timing. The internal resources, such as main memory and the system bus, must be shared among a number of activities, including data I/O. Thus, the I/O function includes a control and timing requirement, to coordinate the flow of traffic between internal resources and external devices. Processor communication. I/O module must also communicate with the processor and with the external device. Processor communication involves command decoding, data, status reporting, and address recognition. Device communication. On the other side, the I/O module must be able to perform device communication. This communication involves commands, status information, and data. Data buffering. An essential task of an I/O module is data buffering. Data coming from main memory are sent to an I/O module in a rapid burst. The data are buffered in the I/O module and then sent to the peripheral device at its data rate. In the opposite direction, data are buffered so as not to tie up the memory in a slow transfer operation. Thus, the I/O module must be able to operate at both device and memory speeds. Error detection. Finally, an I/O module is often responsible for error detection and for subsequently reporting errors to the processor. Example, functions of disk controller, an I/O module. Recognizes messages from device addressed to it and accepts commands from the CPU. Provides a buffer where the data from memory can be held until it can be transferred to a device. Provides the necessary registers and controls to perform a direct memory transfer. Physically controls the device. Copies data from its buffer to the device, or from the CPU to its buffer. Communicates with CPU. I/O module interface. I/O modules perform two different functions. At the CPU interface, the module performs CPU interfacing tasks, accepting I/O commands from the CPU, transferring data between the module and the CPU or memory, and sending interrupts and status information to the CPU. At the device interface, the I/O module supplies control of the device, moving the head to the correct track in a disk drive and rewinding tape, for example. Most I/O modules provide buffering of the data to synchronize the different speeds of the CPU and the various I/O devices. Buffering. A method where a buffer holds the data and release a part of it at particular times. Buffering, holding and releasing parts of data at particular times. A region of memory used to temporarily hold data while it is being moved from one place to another. Buffers can be implemented in either hardware or software, but majority of buffers are implemented in software. Handshaking. A brief back-and-forth series of requests and acknowledgements to request a connection. Handshaking, a process that takes place when a computer is about to communicate with a foreign device to establish rules for communication. If the negotiation is successful, a connection is opened. This connection is logically a full duplex connection. A web browser application uses this technique to establish connection in the Internet. Three-way TCP connection handshake. TCP sends a packet, through the usual network layers, to TCP at the website, requesting a connection. This results in a brief back-and-forth series of requests and acknowledgements known as handshaking. As seen in this figure, if the negotiation is successful, a connection is opened. This connection is logically a full duplex connection, both because web page requests from the browser application at one end node will result in file transfers from the web server at the other, and because TCP requires an acknowledgement packet be sent in return for every packet received. References: Computer Organization and Architecture Designing for Performance, 8th edition, William Stallings, Prentice Hall. The Architecture of Computer Hardware, System Software, and Networking and Information Technology Approach, IRV Englander, John Wiley & Sons Incorporated. Thank you everyone. Stay safe. See you next topic.